Hi everybody, welcome to this webinar about stability. Hopefully everybody can hear me, and now the host for today is mainly me. I will be showing you some examples. I will be talking about stability, but I also have some help with me with Flavio, which I can see now that I've actually pronounced wrong. And I also have Frederick with me. And I also think I actually have another colleague, which is Mohsen. So my colleagues will be able to answer your questions during the chat. And as always, if we are not able to answer all of your questions, especially today, because I think we will be around 300 people joining this webinar. So if my colleagues are not able to answer all your questions, we will reply to them later during mail. So let's start. Well, I will be the presenter. So my name is Siavash. I worked for StruSoft actually 7 years ago, and then I worked for 2 other companies, and now I'm back at StruSoft. So let's start. Let me just, perfect. So for the days today, what we will be talking about, we can start with the basics. General basics about stability, and then we will talk about some applications, how it's implemented. I will show you some tips and tricks how to solve some problems, and of course during the time I will show you examples. So now one of the basics thing, of course, we have to understand is that I think this is a very a good picture that says a lot, and it's that in this case we have that this ball is stable and this one is called unstable, but actually both are in equilibrium. So both are in equilibrium. So by only checking displacements or deflections, you might not get the sensitivity of a structure, and thus comes the instability calculation, to know how sensitive a structure is for any type of instability. And another thing to consider is that we have to, of course, question ourselves what causes instability. Now, the main thing when we are talking about what causes instability is usually eccentricity, but also imperfections. So when checking a cross section, you have to differentiate it between 2 type of centroids. One of them, which is called shear center. In this case, for a C profile, the shear center is located over here, and the other one is the gravity center, or also called centroid. Now, the shear center is the point where you can actually put a load, or you can apply a load which does not cause any rotation at all. I will actually show this with an example. I have a concrete shaft with shear walls that I will show how to get shear center in FEM-Design. But also we have the centroid. So in FEM-Design, you're able to collect these results. And this is how it looks for other type of profiles. But if we check, for example, a regular plan view over here, over the structure, what we can see that we have columns, and these columns are not part of stability. They won't stabilize. They will pretty much just take vertical loads. And then we have shear walls. Now, the shear center of this structure, since everything is stabilized by these 4 shear walls, the shear center is also here in the middle. So what causes instability in this case, or causes forces that might cause instability, is actually eccentricity between the load and the shear center. Now, in a usual case, we have a wind load all over this constant wind load. So the resultant of the wind load is somewhere in the middle. So from this area, so we have here we have the resultant of the wind load. Now, the eccentricity between this wind load, this resultant of the wind load, and the shear center, so this eccentricity, this length is what causes the torsion. So making it, if we take the resultant times the eccentricity here, we get the torsional moment that is caused and have to be taken by the shear walls. So it's very good to actually try to put these shear walls and where we have the load center so that we don't get too much torsion. And how do we find, now the question is, how do we find the shear center, for example, in FEM-Design? And what happens if we apply a load in the shear center? So I thought about showing you a load, an example. So I have an example here with a core wall that I will show you. Let me find it here. So here is this structure. I just pretty much took a simple structure, which is a profile like this, and then I thought about adding the load. So if I would like to know if with a profile like this, in this case, this would represent maybe a shear walls. If I would like to know where the shear center is, what I did was that I applied a shell and applied a diaphragm, and then afterwards I did an analysis, and the analysis was based. I did actually to find the shear center, you need to do an eigenfrequency calculation. This is a way to find both shear center and also the gravity center in FEM-Design. So you can just do an eigenfrequency calculation, and once that calculation has been made, you will be finding some results under the tab eigenfrequency here, and we can find the shear center. So you can see that the shear center is actually located over there. Now what you can see, this black line over here is actually a fictitious bar that I added so that I could add a load on the shear center and make it, of course, interact with the structure. So that's only a fictitious bar. So the shear center is located over here. You can get the shear center from FEM-Design, and also you can also get the total and mass level. So you can also get. Let me put this on wireframe. So here is where we have the centroid in this structure. So this is the total centroid. Now I did draw a line up here just so that I can find where that is located exactly, so that I can add a load on top of it so that we can see how it reacts. But with the theory that I just mentioned, that meaning that if we add a horizontal load at this point, so this is shear center horizontal. If I add a horizontal load at this point, this should not cause any rotation. This should only cause purely translational displacement. And I could also show you how that looks. So if I go to the load case tab and check displacement, I can go to the shear center where I had the load in that point. You can see that no rotation have occurred. So if you apply the horizontal loads where the shear center is located, of course you don't get any rotation. Now I do have also the gravity center, which is over here. So and if I would, in the same point as the shear center, instead of adding a horizontal load, adding a vertical load, then I will actually get a bending moment. This is because for horizontal loads, you have to add the loads. If the load go through the shear center, you won't get any rotation. But for normal forces and normal loads, it have to go through the gravitational center to not cause any bending moment. So if I go to this tab, I can show you also how that translational displacements look when I add the vertical load in the shear center. And you can see I get that deformation. But if I instead would add the vertical load on the gravity center, then I would just make the structure settle pretty much. So this is just a local thing. But that's how it works. That's also how you find the shear center and how you can find the gravity center in FEM-Design. Now let's continue with our examples. So one of the things to think about, of course, when we're doing a stability calculation is that stability calculation have a very basic equation, and it's mainly just an eigenvalue problem. And in FEM-Design, we are using the Langsos method. And one thing to think about is, of course, that stability calculation is actually a linear calculation. But in FEM-Design, you actually have the possibility to run a non-linear calculation, and the program will then gather these internal forces and then run a linear stability calculation with those non-linear effects. And you can also do that with cracked section analysis. So you can actually consider cracked section and the reduction of the stiffness matrix due to the cracked section, and then run stability. So this is actually very, very useful a lot of times that you can do this in FEM-Design. So it's a linear calculation, but you can make it be based on non-linear effects and also the cracked section. And the stability calculation, I mean, is mainly based on just stiffness and loads. And one thing very important thing to understand is that if you have too sparse mesh or too that you don't have enough mesh, then the calculation can get in the unsafe side, especially for bar elements. For shell elements, I would say that I haven't seen a huge difference with the mesh size, but for bar elements, this is very important to think about. So sorry. One second. I think it looks like my screen is you don't see one screen. I think that you're able to see too many screens. Let me see if I can fix this. Sharing here. I'm not sure if that fixed the problems, but we will see. We just continue. So when it comes to these stability calculations, it's very important to understand that having too sparse mesh might yield in results in an unsafe side. So let's continue. And I have an example of this, so I will show you what I mean with this. Now, when it comes to the stability calculation, the result is what you get as a result is actually a critical factor. And the critical factor just pretty much says how much you can increase a load before a certain type of instability occurs. And usually it's the lowest ones that are, of course, relevant. And this will be much more clear when I'm showing an example. But you can also have negative factors, a negative amplification factor in FEM-Design. This is due to that usually these negative factors are not relevant, but they can give some good information regarding the sensitivity. So what a negative factor is pretty much is that if you have a vertical load acting downwards, it will just invert the load upwards, and you might get some negative factors. Those ones usually it's very you don't have to consider them in most cases. Now, so a stability calculation is pretty much compared with Euler buckling calculation. And you have to also understand that a stability calculation is done during ideal presumptions. So we are not considering imperfections, and we are not considering, and we are considering that the load is perfectly centric. So so that's why this stability calculation, it's not a design limit. To consider those other effects as imperfections and that the load is not perfectly centric, we have to, of course, do regular design calculation. So remember that. Now, so when we are checking stability, you have to ask yourself, what should you go as for a limit? We will also delve into what Eurocode says about that. And I thought the best thing is also to start with steel. But the Eurocode in general, it have a limit on when to consider second order effects or not. And I have a PowerPoint regarding second order effects and first order calculation, just to clarify what that actually means. But for steel structures, this is what Eurocode says. Now, Eurocode for steel structures says that if that alpha critical factor, so the amplification factor, is less than 10, then you have to consider second order calculation. But if it's higher than 10, then you don't have to consider it. And remember that this calculation, as you can see here, the FCR, you can see that the FCR is the elastic critical buckling load for global instability mode, so no local. So you should think about that when we do the calculation, we are actually searching for global instability modes. And in a software, we don't differentiate it between local and global. So you have to find a relevant global buckling during the stability calculation. And I will show you how to do that. So I will show you now an example of a steel structure. So let me show you this example. Now, in this example, I have a steel structure standing on columns, and I have a pretty good model here with steel. And designing this, a lot of times when you do a stability calculation, on this, what will happen is that you will get a lot of local modes. So let's see if I have any calculation ready. But so I'll firstly run a stability calculation just to show you what happens when we do that. And when we run the stability calculation, in most of the cases, and also in this case, what you will see is that we will get a lot of local problems. So we don't get these global buckling factors. Give me 1 second. I'll just turn off Skype. Yeah. So what happens is that you will get a lot of these. Local effects, and the solution not to get these local effects is to do some changes in FEM-Design when it comes to the calculation. So as you can see here, if I go to the stability calculation here, and as you can see here is that this is my critical factors, and the first one is 2.8, meaning that I can increase the load by 2.8 times before this instability occurs. But as I mentioned, we are not interested of these local values. We are actually interested of this global instability, not this local. So for this local, for us not to considering the local one and just focusing on the global one, we have to do some changes. So one of them is that we make sure that the column is not divided in several elements. To do that, we go to the settings tab, and I can do that here in the structure tab. So to do that, I go to the setting tab, and then calculation, and over here I'll go to the mesh, and in the element tab you can see that here I can set the bar element parameters. So this is the default minimum division number. So how many times the column should be, you could see, divided. And you should have this value not more than 1. And I think I showed that in this PowerPoint. So this is when we have the value 2. What it will happen is that it will pretty much divide it in 2 elements. And what will happen also is that the buckling shape will in that case look like this, because we have 2 different elements and it can buckle in the middle. So we have a node in the middle, but we do not like to have one mode in the middle. So we will just use a value of 1 in a minimum division number. Now remember that when we do 1 here, this is a change we make for all the columns, for all the bars in the structure. So once we do this calculation, this is a general setting for all the bars, but you can also in the finite element tab set different division number for different elements. So the first one we set was a minimum division number. And now we make sure that even all the other ones, even the local ones, I mean all the bars, do not have a division number that is more than 1. So you can set this by using this function minimum division number and choosing all the columns in the structure. And you can here actually just type the number 1. And what will happen is that it will override all the division numbers to just 1. And the one last step to do to avoid these local instability and just have global instability is that when you're doing the analysis calculation and you're inside calculate here, in the analysis tab, make sure that the finite element tab that you choose is not fine element, instead standard elements, because this fine element will actually cause a node in the middle. And we don't want that node in the middle because we don't want this local buckling. So I just changed this to this type. And then let's run a stability calculation just to see, did we, by these kind of changes, are we able to find a global instability mode or not? So, also remember that I mentioned before that when the minimum division number is too little, we also have another problem. And that problem is that we might overestimate the stiffness of the structure. But we can see that now the stability that I get is actually a global stability. And you can see how that stability shape looks like. Now remember that this value is 6.8, and for this, now right now they are divided in just one element. So you can see that the shape is not a curved one; it's very linear shaped. So we should make sure that the parts that are buckling should have enough division numbers. But how do we then how do we create enough division numbers without getting local instability of the columns? One solution is that, of course, is that when we are in the finite element tab, we pretty much just take this division number and we only change it for these elements above and not the columns, so that I don't get any local buckling for the columns. So I can just change all of these to, I'm gonna just put a value of 10, which is good enough. And then I'll run a calculation. Now, before the stability value had a value of 6.8. So now let's see what happens when we add more division numbers and more nodes in a bar element. So what happens then? And of course, we should get a better value or a more critical value. So we should get a lower critical factor, because if it's too sparse, as I mentioned, you get higher stiffness. So what we are actually doing here in this example, what we did is that, let's check the result, and we can see that when I check the stability, the value now have gone down from a value of 6.8 to 4.2. Now you could increase to more division numbers, but you would probably get very insignificant increase. So, but it is always good to do a convergence analysis and try with a higher value just to see if something will happen. But probably this is a value that you can use. So when it comes to steel structures in FEM-Design, you can actually consider, now in this case, this global instability is less than 10, which means that you should actually consider second order effects. Now you can consider second order effects in FEM-Design by actually activating imperfection calculation. So especially for steel constructions, steel structures, you can activate imperfection calculation. What happens then is that the program will automatically add all the imperfection that is needed, and you have to, of course, once you've created imperfection calculation, you will get these shapes as we got right now. And imperfection calculation is very similar to a stability calculation. The difference is that it will add imperfection shapes, so real imperfections to consider for second order analysis. So in FEM-Design, you can consider that without any problem. One thing to think about is that there is actually two ways of considering second order effects. Now, do not mix second order effects with second order analysis. It's two completely different things. Now, there is two ways of considering second order effects. One of them is by actually just doing a first order analysis calculation, as we did right now. But what will happen when you do this is that when you design the column or the beam or the structure, what happens is that the second order effects are added in the design checks. So when you do a first order calculation, the second order effects of a column or the buckling effects are added in the design checks, including the imperfections. But if you do a second, but sometimes, as I mentioned, you cannot do a first order calculation. You have to do a second order calculation. And in those cases, when you have a alpha critical factor that is less than 10 and you have to do a second order calculation, then in FEM-Design, when you activate second order calculation, what it means is that you're actually considering the second order effects. But in this case, you're considering it during analysis. So in the first case here, when you do first order, it's considered during the design check. In the second step here, you're pretty much considering those second order effects in the analysis. Now, let's get back. So we have the first order calculation, and then we have the second order analysis. The first order calculation, which is this one I'm talking about. In this case, remember that initial bow imperfection is included already in the design. What you need to add manually when you do just a first order calculation is that you have to add a global imperfection. When you're doing a first order calculation, initial bow imperfection is pretty much considered during the design check, but you should add a global imperfection, which is the deviation load. And in FEM-Design, there is possibility to add deviation load automatically. If you run a second order calculation with regards to FEM-Design's calculation and the imperfection that FEM-Design does, then you're actually considering within that calculation both the initial bow imperfection, the local imperfection, and the global imperfection. So you actually don't have to do anything more than that. So when running a second order calculation in FEM-Design for steel, you're getting both effects if you run an imperfection calculation. Now, when it comes to concrete, there is it's not 100% clear in the code how to solve these problems, but I was able to find some guidelines regarding this. In Annex H of Eurocode 2, which is an informative annex, you can see that they have some guidelines regarding global second order effects in structures. So they are talking about these flexural, you could say flexural or bending deformations, and then you have the shear deformations over here. So they together both have to be considered. But as you can see here in this part, it says that global second order effects may be ignored if the following condition is fulfilled. And the value that they use is 0.1 times FVB. And the FVB is the global buckling load taking into account the global end bending and shear. And FEM-Design considered this during the stability calculation. So it, of course, considers both bending and shear. So 0.1, this will give you actually the same. You could say that it will give you the same as steel. I mean, it's 0.1, so it's 1/10 of that value. So at least when I did calculation in structures, I usually also used that. As long as I have alpha critical factor that is higher than 10, then in those cases I did not consider second order effects when I did my analysis. So there are some guidelines to check, but when it comes to that, you have to be very careful with what stiffness you put on concrete. So especially when you have a cracked concrete. Now there is a guideline also in Eurocode that says that if there is an absence of more accurate evaluation of the stiffness, you could assume that a cracked section will give you 0.4 times the stiffness. So you have pretty much just 40% left of the stiffness of the concrete if you allow for cracking. So this is a very, you could say, a simple way without doing more accurate evaluations. And you also have to consider that the elasticity module that is being used here is ECD, which is the medium elasticity modulus divided by this factor, and this factor is equal to 1.2. So this is at least what Eurocode says about this. Now, how should we solve this in FEM-Design? How can we reduce the stiffness due to cracks, and what ways can we use? And one thing to know is that in FEM-Design, different analysis requires different type of elasticity modulus that is being used. So you can see that during the stability analysis, it's been using F, which is this is stability times the ECM, which is the elasticity modulus, this one. And this one, but we are supposed to use ECD, which is divided by 1.2. So you have to consider that when you do you have to make some reduction for the stability, and I will show you also where you do this stiffness reduction. And another thing to consider, so the things I mentioned here, I will talk about it shortly, but I thought let's talk about creep also. So we will talk about, we just spoke about a little about cracking, but now let's talk about a creep a little. When it comes to creep, you can see that according to this is that the creep deformation due to, at least if you have the main load, if the main load is wind load, you can see that you can calculate the effective creep value during this ultimate limit state as the bending moment of that is caused, or the moment that is caused by the wind load, for example, in quasi-permanent state. Now, in quasi-permanent state, the load is almost zero, you could say. So in most cases, you could pretty much assume that at least if you have the wind load as the main load, that the creep is not really governing in those cases. It's actually more important to think about cracks, because that's where the real reduction of the stiffness comes. So creep is not governing, at least when you have wind load as the main load. Yes, but I thought, let me show you an example of a concrete structure. So I'll pretty much show you, this example where I have a structure over here with shear walls in the middle, and you can also see that there is an opening or some openings here just to create different stiffness in this side than we have in the other side. So how would we consider this building for stability? Now I will show you which ways that I used when I was doing a lot of these design calculations. So First of all, I did not want to consider any local buckling modes, so I did not want to consider these local shapes. So to remove those local shapes, what I did was that, as I mentioned, I went to the settings, and in the settings, for all the bar elements, because I don't want to consider local buckling of the bar elements, for all the bar elements, I went to the mesh tab and changed this to 1. Make sure that they cannot buckle in the middle, so that I only get these global shapes. And then afterwards, I went to the finite element tab and I made sure that these minimum division numbers, I chose all the elements here, and I changed the minimum division number to just 1. And after that, when I did the analysis, of course, I did the last step, which was that during the analysis calculation, I made sure that this value is set to a standard element and not these fine elements, so that I don't get a node in the middle. And then afterwards, I ran the stability. And then as you can see in my calculation right now, the first shape I get is 20. And you can see that it's a global instability. Immediately I got a global instability shape, which is what I actually wanted. Because these factors are based, when you're checking them, if you need to do a second order calculation or not, they are based on global instability modes, should be based on global instability modes. So you can see translation. So here you can see these different types of instability shapes. And here we have a rotation that occurs. So what I also did was that when I went to the concrete walls, what I usually do when I do the design, of course, you have to check your own design to see if that's implementable in your case, but I put a reduction value of 0.33 to consider cracks. Now, I did show you during the PowerPoint that that reduction factor, according to this, should be 0.4. But since since you're using ECM, and ECM is supposed to be divided by 1.2 to get ECD, because you can see during this stability analysis that during stability ECM is used and not ECD. So to consider ECD here and considering the 0.4 factor, together you get a common factor which is approximately equal to 0.33. So that's why I put this value in this. So this is the reduction for stability analysis. This is the factor where you can actually reduce the stiffness during the stability calculation. So here you can, this is the stiffness modifier, with other words. So by changing all of the concrete elements in the shaft, I considered pretty much for just to be safe in early calculation that everything is pretty much cracked. And I wanted to make sure that even though that's the case, I do not have a shape that is lower than 10, because if it's lower than 10, then you have to consider second order calculation. But in this case, as you see, I did not have to. That means that I can continue with my linear calculation. I can continue with my first order calculations. So that's at least how I solve the problem. So creep is seldomly governing when you have at least wind load that is the main load. And I also took a picture of another project that I was working with, and in this project I did the same settings. I changed the values so that I get these global effects, and you can see that I got these global, and then I checked, of course, the critical parameter to see if I have to consider second order effects, or if I have to do a second order calculation or not. And I saw that that was not a problem. So in this case, I got these different shapes. So that's actually what I wanted to show in that case. Now, another thing I thought is very good to talk about is that I've got some questions before regarding using a bar element instead of using shell elements. So And I have an example of that I can show you. So what happens when you're using, for example, let's say if you have a shear wall and you're having a bar element, you design it as a bar element instead of shell element. So in FEM-Design, one of the unique things in FEM-Design is that you can actually create any shape. So for example, this shape of concrete, I could create as a bar element. I could actually go to the tools section editor, and there is a tab here called, now where did I put the section editor? Here it is. So you can create any arbitrary section and the program will calculate this, the material properties and stuff like that. So what I did was that I wanted to show you when if you can, when you should not actually use bar elements, because the checking stability for a column is not the same thing as checking stability for shell elements, and especially when you have some effects. And I will show you now an example where I have a wall. So I have a simple wall here, and in this wall I added a line load, and I want to see the stability shapes of this wall, and then I compared it to when I have a column. So I have the same column here, but you can see that the column I created with section editor is the same column. It's 4 meter wide, 200 millimeter width. So I added the same load. So the same load is applied, and then I wanted to check the stability shapes. Now, if the governing shapes, or the first shapes, I would say, that you get is something that is pretty much causes simple longitudinal flexural shapes, or translation deflection. If the load causes instability shapes that are purely translational, then you will get the same value when you have a bar element and when you have a shell element. But that will not be the case when you have rigid body rotation. I mean, if you have any rotation or you have any distortion or warping of the section, because bar elements do not consider these ones the same way. So especially not distortion and warping, they are not considered pretty much at all. So you have to think about that when you compare those two, some shapes will not be governed. So, and I will show you in this example how this looks. So let's take a simple wall. Now in this case, I pretty much go to the stability calculation. Now let's check the first stability calculation. You can see that the first one is 21. So that means that if I increase my load with 21 times, I get this first shape, which is of course a flexural deflection in the weak direction. And if I would do it the same with this one, so you can see that I get pretty much exactly the same result. So they are equal. You can see that a wall and a column, they will give the same shapes. And if I go to the next one here, which is this shape, and let me just amplify this shape so that we see how it looks. And we can see that they are pretty close, 197, 195. This will also be the same shape. So it's pretty much the same shape in both cases. So they can be used, but you have to think about that there are some shapes as torsion and warping that is not considered when you have regular bar elements. And I will show you how one of those shapes can look like. So as you can see now, so far we've had the same shape, but as soon as I find another shape, which is, for example, like this one, which is rotation, this shape will not be found by a bar element. And this is very important to know, because if you're now in this case, this was the fourth shape. Now the lowest that you have is of course what you design for usually, but it could be that you have a structure where this shape would be the first one, and this will not be found with a regular bar element. So if there is any possibility of rotation or warping, you should have a shell element instead. So you can see that my next shape here is this one, and this is the fifth shape of this one. So it jumped over the fourth shape because a bar element will not consider torsion and distortion of the section and warping. So make sure that you are considering that correctly. So easily said. I mean, if you have that that these ones are not governing in your case, then of course you can just do it as a regular bar element, simplify and check it like this, and maybe using the shaft and drawing it as with the section editor and creating a concrete column, you could say, and designing it like this. But remember that if these ones are governing, then you might miss out of those shapes, and this could be critical in some cases. So yeah, so that was that. I think that was the models I wanted to show you. Let me see if I was able. Yeah. So those was the model that I wanted to show you. So if I would summarize a little, let's go back a little, and I will summarize what we've been talking about. So let's quickly summarize. So what we spoke about is that the shear center, this is something that you can find in FEM-Design by doing eigenfrequency calculation. You can find where the shear center is, and you can also find where the gravity center is. And also is that that you have to think about not having too sparse mesh, because that might yield result in an unsafe side because you overestimate the stiffness. And you also have to think about that this is not a design limit, and that for steel, Eurocode is very clear cut. It says that we can follow this value for elastic analysis. So if we have a critical parameter that is higher than 10, then we don't have to consider second order analysis calculation. We can just do a first order calculation. That's good enough. And one solution to not get these local problems is to divide the elements in just one, or not dividing it at all. So you should put 1 in the division number. And of course, the difference between first order and second order calculation is that what you need to think about is that the first order calculation, global imperfection, you have to add it manually, or you can add it with FEM-Design's function, which is called a macro load, where it calculates what deviation load you have, what global imperfection load you should have. And if you do a second order calculation for steel, you can also connect it to an imperfection shape, and then everything will be considered, both the local shapes and the global shapes. And of course, in the Eurocode, there are some guidelines. You should go through these ones a little specifically, but you can see that you can use approximately this stiffness to calculate. So in my case, I used 0.33 because 0.4, and then this value was ECM divided by 1.2, which is this one. That gave me 0.33. So I used that factor to consider that the section is cracked. If the section is not cracked, you can actually use the 0.8 value, but in that case also you have to reduce it with ECD value. So if the section is not cracked, you can use the 0.8. So you should try to, in most cases, actually reduce the reduction. You should reduce the stiffness in both, even though it's cracked or not cracked, you should reduce it. But in FEM-Design, you can also do more accurate calculation considering crack section analysis. Remember that instability analysis, this F-stab is used, and the mean value of the elasticity module is used also. So consider that you need to use ECD instead. And the creep factor, I mentioned that for wind loads, in most cases, this is not governing. It's very seldomly governing. It's mostly crack that we have to consider. So that was those, and you have to consider that when designing with bar element instead of shell element, you should know that some effects are not considered the same way. So these type of shapes will not occur. And if this is the first shape that will occur, then your calculation might be based on wrong stability factor. So make sure that if you do a column calculation instead, make sure that these type of shapes are not governing. But one other thing that is new in FEM-Design that you should also know about is that sometimes it's not that sometimes it's not the column that might buckle locally. It could be a shell element that buckles locally. For example, in my case, when I had a lot of steel structures, I used a trapezial steel sheet on top of buildings. And I got a lot of different buckling shapes in the shell element, and I really didn't want them in my shapes because I'm supposed to consider buckling shapes. So what you can do if you have these buckling shapes on a shell element or even at a wall element, you can actually create, you can replace that area or you can replace that shell with a profiled plate. By replacing it with a profile plate, I mean, you could put a regular 200 millimeter concrete with the same stiffness, but by doing it, replacing it with this, you have a new function in FEM-Design that is implemented recently, and this is this one, which is called ignore instability and imperfection calculation, but take account into its rigidity. So with this one, these local buckling will not occur. So it will pretty much ignore it. So I had one case where I had only the wall locally in a story that wanted to buckle. This was not a global buckling. So what I did was that I replaced the wall by actually creating a profiled wall instead. And if the wall was 200 millimeter thick, what I did was that I went into this tab and I used section, and I used a regular concrete section, and I used a rectangular section. So 200 millimeter tab, and the length is not important because you draw the length yourself because this is a profiled wall. So by doing this, I considered the correct stiffness, but I was able to remove it from the stability shapes. So this is a very good trick to use when having these local shapes. You can replace them with this one. Okay, so that was, I guess, all that I wanted to say. Hopefully, I know that sometimes I have a tendency of speaking too fast. But so that was it for me. And hopefully my colleagues are able to answer your questions. And if not, of course, we will get back to you with a mail. And I can see that there is a lot of questions there. So I thought at first that maybe I should just take a question and respond to it here, but there is a lot of questions. So in this case, what I will do is that I will get back to you. I will talk to my colleagues and we will get back to you with the answer to all your questions. And you have my mail also, and you have our mail. So let's go get back. So you can find my mail over here and my colleague's mail over here. So just let us know if you have any questions. Hopefully this was something new and you learned something new today. Thanks for your time.